So I'm going to work with the metal ball. It's arbitrary. I could switch back and forth since the mass doesn't matter. But let's work with the metal ball, because what I'm going to do now is change the length, and since they're both the same, it doesn't matter which one I work with, right? So let's change this from 50 down to 30. We're measuring from the bottom. The bottom of this ruler, right, it matches the center of gravity of that ball. So at 10, 20, 30, let's change the length down to 30. And we're going to, again, time 15 swings. Let's get ready. 3, 2, 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, stop. 16.64. Okay? So this was at 30. I'm sorry. This was at 50. And the large mass at 30 is 16.64 seconds. You can find the T1 by taking that 16.64 divided by 15, since that's 15 swings. Now, let's try another length. That was 30, we have done 50, let's try 70. 10, 20, 30, 40, 50, 60, 70. Ruler's back, that's okay. So, let's try 70 now. Do you think it's going to swing faster or slower at this longer length? Well, let's try. Let's get ready. 3, 2, 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Stop. 25.02. So at 70, and we're going to try one other length. Let's take 100, the full length of this ruler. Right? Now looking at the pattern that has emerged so far, for 50 centimeters, the time was 21.25. For 30 centimeters, it's dropped down to 16.64. For 70 centimeters, it's 25.02. So we can expect 100 centimeters to be much longer. Right? So let's try. 3, 2, 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Stop. 29.79. So at 100, the time for 15 swings, 29.79 seconds. So T1 for 100 is 29.79 divided by 15. In other words, almost 2 seconds. Okay? So, One last question before I let you go and run through the calculations. And on the lab sheet, you will have the data spaces, the spaces for you to put the times, the period. Remember, the period is the time for one swing. You would take all those times and divide by 15, those numbers, and divide by 15. And then I want you to explore the possible patterns. Notice it's the length that determines the period, not the mass, not the amplitude, but only the length. And of course, I must add, that is true if you keep the angle of the swing small. If we make that angle very, very large, then another factor comes into play, because a pendulum is really not a simple harmonic oscillator. It mimics a simple harmonic oscillator at only very, very small angles, less than 20 degrees. When you get this thing up to 30, 40, 50 degrees, then the effect, the rotation of the Earth will affect the swing, and it starts to swing around in a little circle, and that is the effect of the Coriolis force, the Earth rotating from underneath the swinging pendulum. But that's another story. If you want to study that kind of stuff, take a real physics class, and you can explore that in more detail with the full mathematics that governs the swing of the pendulum. But anyway, those are the calculations that we have. Calculate the period for each, and then for the lengths, the 30, 50, 70, and 100. Okay? Search for the pattern. Now, here's the question, the last question. The length, for a length of 100, you have a period of 2 seconds. What length do you think will give you a period of 1 second? You see, if you could do that, if you could make a pendulum that would give you a swing of 1 second, you could make a clock. And that's what Galileo did. 1600, he made the first clock. Of course, I don't think he's given credit for making the first clock, but he explored the relationship between the period of a pendulum and the length of the string that the bob is on. And then I think it was Christian Huygens that actually made that into a clock. But it was the physics, the engineering, the work of Galileo that allowed other people to come along after him, not long after him, and to perfect the mechanics of a clock mechanism. But it was using Galileo's study of a pendulum to do that. Okay?